Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe. So here is the 14th solution by method of consistent deformation and by the matrix approach. So originally there is a ruler support at B because this is statically indeterminate to the first degree, and I remove support B so that we can compute the deflection at B by the matrix approach. So originally there is a support at B, ruler support at A. That's why it is required to determine the reaction at A, vertical reaction at A. So having removed the support at B, it will now deflect as shown, and we'll call the deflection as delta B. The fixed moment at A is 18 W 10 square over 12, so 150 counterclockwise because this is supposedly negative from slope deflection equation, and here it is 150 as shown. Then because of symmetry, FA is WL over 2, 18 times 10 over 2, so that's 90. FAR, then FB left is also 90. Then for BC, fixed moment is here counterclockwise, 36 times 4 square over 8 square is 36. Then this is also 36, but clockwise. Then FB right is half of 36 because the load is at the center. So 18, then this is also FC left 18. Although not important because we would just want the deflection at B. Now the stiffness of the elemental stiffness of AB from matrix structural analysis is 12 EI1, or let's factor out EI, over L cube. So 12 EI over L cube. So 12 times EI for AB divided by 10 cube is 3 over 250. Then the next is 6 times EI, 1 over 10 square, so 3 over 50. Then the negative of this cell here, then you just copy 3 over 50. Then this is 6 EI over L square, 4 EI over L, so that's why it's 2 fifths. 4 times 1 over 10 is 2 fifths. Then the negative of this cell, then half of this value. Then AB, or node 1, node 2 is 1, 2, 3, 4, 1, 2, 3, 4. Then the third row is the negative of the first row. The fourth row is we copy the second row except that we interchange position 2 fifths and 1 fifth. So that's it for AB. For BC, it is EI quantity. It is 3, 4, 5, 6, 2, and 3. So 12 times EI 1 over 8 cube is 3 over 128. 6 times 1 over 8 square is 3 over 32. Then the negative of that cell, then copy. Then 6 EI over L square. 6 times 1 over 8 square is 3 over 32. 4 times EI 1 over 8 is 1 half. Then negative of that cell, then half of 1 half is 1/4. Then the negative of the first row, then second row, except that these positions are interchanged. So that's it for stiffness of elemental stiffness of BC. Then for the global loadings or forces at node 1, 0 minus 150. So we have negative 150 or 150 clockwise as shown. At B, we have vertical load of opposite to this, 90 plus 18, so negative 108 or 108 downward, and 150 minus 36 is 114. Since it is positive, so it is counterclockwise. So we have 108 downward kilonewtons and 114 counterclockwise. Then at C, 36 minus 0 is 36, so 36 is positive, so it is counterclockwise only at C. So take note that there is 108 here because I removed support B, so it will deflect downward, and the deflection is denoted by U3. Then at A and B, there's no need to apply this downward force because these are supports. So the nodes 1 and C will not move downward. So we are interested only of 2, 3, 4, and 6. So these are the nodal global forces, and this will be the structural elemental stiffness or the global stiffness for 2, 3, 4, 6. So we have 2, 2. We have 2, 2 here, which is 2 fifths only. So that's why it's 2 fifths. 2, 3. 2 and 3, negative 3 over 50. 2, 4. 2 and 4, 1/5. And 2, 6. None. So that's why it's 0. So we copy by symmetry. Negative 3 fifths, 1/5, and 0. And 3, 3 again. We have 3 over 250 plus 3 over 128. So that's why 567 over 16,000. And so on and so forth. So you just put the values here. And then we can now compute U2, U3, U4 by your calculator, because the calculator is capable of solving 4 simultaneous equations. So U2, U3, U4, U6 is the product of the inverse of this structural stiffness matrix times these global forces. So using the calculator, we find U2, U3, U4, U6 equal to these values. Then delta B is U3, and it is negative 50,320 over 3 EI. Then for the second part, we have to apply a unit upward load so that it will deflect FBB. The displacement is FBB. Since originally we consider AB, and since the load is acting at the end, and we imagine this, so there's no fixed moment in AB, there's no fixed moment in BC. So 0 here, 0 at C. So the only loading is upward, and that's 1 kilonewton. These are supposedly the reactions. So loadings, U2, 0, U3, positive 1, U4, 0, there's no moment here at B. Then U6 is 0, there's no moment also here. Then same value of the structural stiffness matrix, except that the corresponding displacements are denoted by FU2, FBB. We are interested of FBB, the vertical deflection here. FB theta, the slope at B due to this unit upward load. And FU6 means the slope at C. FU2 is the slope at A due to this unit load. So again, computing these displacements, the product of the inverse of this matrix and these global forces, the result would be as follows. So FBB is 3,200 over 27 EI, so positive as shown. Therefore, by compatibility equation, FBB times RB plus delta B equals 0. Substitute 3,200 over 27 EI plus RB times RB plus negative 50,320 over 3EI equals 0. So RB can now be computed. So considering the entire system, take note there is support here. So RA times 18 plus RB 141.525 times 8 equals 36 times 4 plus 18 times 10 times 13. So RA times 18 plus 141.525 times 8 equals 36 times 4 plus 18 times 10 times 13. From there, we can solve RA equal to 75.10 kilonewtons. And for your part, I want you to solve this problem in the same manner here and show that RA is 125 over 18 kilonewtons or 6.944 kilonewtons.